have a look while we're going. Okay, welcome to Sheffield. And I don't know, I've lost count of the number of editions of Gaussian Process summer schools. So this is one in a series. And the tradition is normally to do I do a kind of basic motivational introduction and then a more advanced introduction which will be given by Rich. It always seems more advanced. That wasn't the original intention. Okay, so, and if you have worked in Gaussian processes before, you'll know that this is still probably the one of the most important books. The nice thing about it is it's also available freely as a PDF online. It's about 12 years old now, but it has a lot of the sort of tricks in there. I always like to start my slides by just a reminder of what machine learning is, because I think one of the things that we forget, we spend a lot of time talking about models. But machine learning is a combination of data and model. And certainly when you look in industry, you find that most people spend most of their time trying to fix data and get the data right. And the models, actually, in terms of time spent, is only 20% of the equation. But the model is the main thing we're going to talk about over the next few days. And the model is, of course, critical. So data, I think of data very generally as it could be actively or passively acquired. One of the things we're seeing now a lot is, of course, you get streaming data, like clickstream data, sort of sequentially arriving data. But it could also sort of be data that you have actively looked for, rather than just passively given. The model is your assumptions that you're going to use. Now, I've said machine learning at the top, but actually this could also apply equally to a number of fields, including, say, statistics. I would think in some cases also control theory, econometrics. There's just a range of fields that are doing the same thing, combining data with some modeling assumptions. The difference between these fields often is either the nature of the model they use, or how seriously they look at things like interpretability. So in machine learning, the focus has traditionally been very much on accuracy of prediction, rather than the interpretability of the model. But what you're seeing now as these models are being deployed in practice is people are actually starting to look at interpretability. In statistics, I would argue that the focus has been more on the interpretability of the model and less so on the sort of pure accuracy of prediction. So you tend to often get simpler models and more time spent trying to interpret them. So the model I think of as including our sort of belief in the regularities of the universe. And a typical assumption is smoothness. So you would sort of be surprised if I disappeared from this side of the room, reappeared on that side of the room. That's because you're making smoothness assumptions. And they are often very useful in practice. So you can have much stronger models. So there's many fields where you write down a very complex model, but they're often harder to combine with data. So what you very often find in machine learning is that the model is what I would call weakly mechanistic. It doesn't contain very strong mechanistic assumptions. It just contains looser assumptions like smoothness. And then the objective is to make a prediction. Now, a prediction could also be a sort of action to be taken, and that's the sort of thing you might get in robotics. But it could be a categorization, like in image recognition or face detection in image. Or it could be a quality score, like a lot of people used to do quality scores in gameplay before the sort of AlphaGo. People were quality scoring the quality of a game position on a board as a way of doing games. Okay. So we'll just look at some data, which actually I'm not going to look at, because I have follow-on slides, but I won't look at this too much anymore. But the type of issues you get with data can be seen in this Olympic marathon data. So this is data from which I use quite a lot, which is just the pace of marathons run across different years. And the sort of thing you might be looking to do is predict what the pace of a marathon would have been if there had been marathons during the Second World War, or indeed during the First World War, or back across time, or forward into the future. So this is the typical one input. I mean, I choose this because it's one input, one output, and you get sort of characteristics like here. There seems to be a big outlier. Like I can run a marathon in about that speed. But you know, it'd be achievable for me to win that Olympics. Only it wouldn't have been because they got lost in that Olympics, and cars had just been invented, and they had cars in front of the just been invented, but it just become popular in front of the runners, and they were kicking up a lot of dust, so the runners were breathing in a lot of dust, and in the end, only 6 people finished. So. Of course, nowadays, what's interesting is you see this larger noise, and then you see sort of things changing over time to a narrower noise. Okay. So how do we deal with that sort of system? Well, first of all, I want to introduce the sort of notion of an overdetermined system to try and sort of understand a little bit, dig down into how we're doing typical modeling. It's a review of things that most of you have seen before, but unless you've seen me talking, which you might have done, then it's presented in a slightly different way. So very often we're trying to fit a line, and in this case I've formulated a line which we might be trying to fit to that Olympics data to some data. So I've just drawn a line here, and it's got a sort of gradient which is given by m and an intercept that's given by c. That's standard sort of high school equation for a line. Now, what I want to emphasize is what seems obvious to us today was not obvious to the first people who looked at fitting data, and it's worth sort of thinking about how they looked at things. What they looked at is, okay, if I have 2 points, I can solve a set of simultaneous equations, and I can recover m and c because I've got 2 points and I've got 2 unknowns, so I can write down 2 equations, and then I get the line that goes straight through these points. So I can take point 1, I can take point 2, I have 2 simultaneous equations. But what happens if I get a third point? So if I have a third point here, now I can't fit a line that goes through those points. Now you might all think, oh, this is easy, I'm just going to do least squares or something like that. But when people first observed this, they were looking at, or certainly an early motivation around this area, was they were trying to plot the position of planets that they were tracing in the sky, find the equations of their orbits, and what they would find is they would make multiple observations, and then they couldn't fit their equations directly to the data. And many, many different things were suggested for how to do that. So now there's sort of 3 possible lines you could consider. And people sort of said, well, what should we do with these? We could average them, or we could try and find a median. And people had arguments for and against different approaches. The person who, by my understanding, made most progress on what to do was this guy, Pierre-Simon Laplace. So what Laplace did is he said, okay, let's somehow I have to move that around to get it up. Oh. Sorry, 1 sec. If I refresh that, that should come up. Okay, so this is Laplace's book, The Philosophical Essay on Probabilities from Google Books. And Laplace is famous for this statement, which is a bit too small for you here, but I can read it. It says, "Nous devons donc envisager l'état présent de l'univers comme le fait de son état antérieur et comme la cause de celui qui la suit." Now, where's Nicolas? He gets annoyed with me every year for butchering the French. And but of course, I have the English instead. We ought then to regard the present state of the universe as the effect of its anterior state and as the cause of the one which is to follow. Given for one instance an intelligence which could comprehend all the forces by which nature is animated and the respective situation of the beings who compose it, an intelligence sufficiently vast to submit these data to analysis, it would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atom. For it, nothing would be uncertain, and the future as the past would be present in its eyes. Okay, then he goes on to say the human mind offers, in the perfection which it has been able to give to astronomy, a feeble idea of this intelligence. This is, for me, this is fascinating because, I mean, it's a glorious paragraph. It's quite famous. Does anyone know what it's called? It's called Laplace's Demon. and it's also known as Laplace's determinism, and it's referred to as sometimes the clockwork universe. So he's saying we ought to regard the present state of the universe as the effect of its anterior state and the cause of the one which is to follow, which in a loose way of saying is kind of the Markov property, which is actually described by Markov about sort of 80 years later. Given for one instance an intelligence which could comprehend the forces by which all the nature is animated, that's the model, the forces by which nature is animated, and the respective situations of the beings who compose it, that's the data, the beings that compose, the respective situation of the beings that compose it. And if intelligence sufficiently advanced to submit this data to analysis, that's compute. It would embrace in the same formula the movements of the greatest bodies of the universe and those largest atoms. For it, nothing would be uncertain in the future as the past would be present to its eyes. So he's saying then you can get predictions, sort of absolute predictions, which is an extraordinary statement. And it's often quoted as a sort of naive thing Laplace said. But people who say that themselves are a little bit silly because actually that's a straw man. Laplace sets that up on page, so this is the book again, that's page 3 in the French text. This is page 5. And he says here, well, I'll just do the English. The curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge. So that's a less sort of quotable paragraph, but that's actually the point in the essay. The essay is called A Philosophical Essay on Probabilities. It would be odd if he was saying that you should model the whole universe as deterministic, although everyone says that's what he says. Actually, 2 pages later, he says, we can't do that because of ignorance. We have ignorance about the model. We don't actually know the forces by which nature is animated in totality. If we're looking at simple physics models, we might be okay, but if we start looking at complex biological models, it's difficult. We often have missing data. And that's what he's sort of talking about here. He's saying if we're looking at a molecule of air, we can't measure to a fine degree those things. And what he's saying is we deal with that with probability. And the rest of the essay goes on to talk at length about probability. So how did he deal with this? And he's famous for looking at this situation. He said, OK, so what we'll do is we're going to introduce a latent variable. We're going to say that the observed data is equal to the input times some scale plus some offset plus some thing that I don't know. That's where he's putting the ignorance. So now you have 3 equations, but you actually have 1, 2, 3, 4, 5 unknowns. So in a very clever trick, he converts an overdetermined system into an underdetermined system. And what he does next is then he deals with the underdeterminedness with using a probability distribution for this variable here. What he did not use was the Gaussian, actually. So Laplace actually, so de Moivre is the first to write down the Gaussian as a approximation to the binomial distribution, but Laplace didn't know about that, and he independently wrote down the Gaussian. He wrote it down for something called Laplace's approximation, which is an approach to Bayesian inference where you're fitting the curvature of the posterior, and not in this context. So he wasn't the first person to say use a Gaussian distribution for this. Gauss was, and that's why the distribution is sort of named after Gauss. But Gauss actually credits it to Laplace, says this is a distribution Laplace came up with. Laplace himself worked very hard to try and find what they would call an error distribution, which he could come up with from his principle of least, what's his principle called? Principle of least stuff. The name escapes me. His idea that it was like a maximum entropy principle, that you should add the least information to any situation, or they didn't think about it in terms of information. And he worked hard to come up with error functions of that form, but they were very difficult to compute with. So in practice, the person who sort of described this as the error function was Gauss. So Gauss certainly didn't invent this distribution, but he used it in this form where he said that if I believe that the function I'm interested in here is corrupted by Gaussian noise, then I can sort of substitute that function in to the mean of a Gaussian distribution. And in the probabilistic view of machine learning, this is how we would write it down. So we say that our observation is given by a sort of mean function, we would call this, and some variance, which it departs away from the underlying distribution. So that's known as a noisy function. And it also can be seen as a stochastic process, although it's not a very interesting one because it's just adding noise to a sort of deterministic process, f of x. But that was the basic idea, and this is how Gauss became famous. Gauss was 23 when he refitted the orbit of the dwarf planet Ceres, which was thought to be what they called a main planet, a Haupt planet, and in the sort of literature at the time, they'd lost this planet Ceres, and Gauss managed to take observations they had made by a guy called Giuseppe Piazzi, and he fitted the model, which was a model for planetary orbits, which is slightly difficult because you've got to take into account the Earth rotating and Ceres moving around the sun and us moving around the sun. So it was actually a form of basis function model to the observations, and they were able to recover the location of the planet a year after it was lost. It's an amazing story because they managed to, within the space of a year, find a planet, lose it, publish the data. Several people tried to recover it, and then within the space of the year, someone was able to recover it. And this was all back in 1801, so there was no internet. So it's amazing how fast they could publish. I mean, there weren't even railways. You know, there were canals in some advanced countries. But you know, it's very difficult to communicate, and Piazzi himself was in Sicily. So it's extraordinary how fast they managed to recover this planet. And it took Gauss, I think, 2 months of maths to get the fit. He managed to reduce that to a month. And that's why it's called the Gaussian distribution, because I guess he was 23 years old and became very famous at that point. So it's the distribution I hated most at school. It's the piece of maths I hated the most because I didn't understand how my life was going to be spent playing with it all the time. And I'll sort of say why I didn't like it very much and why I find it super interesting now. When I was at school, Gaussians seemed to be just about computing the mean of data and then the standard deviation. And that was as far as I could tell. Well, the mean was easy to remember as a formula, and the standard deviation you had to think a little bit, but it didn't feel like real maths. But of course, nowadays, I find you can do real maths with the Gaussian. So a classical Gaussian would have a mean and a variance. And I'll tend to write it in that form, a Gaussian over a variable y with mean mu and variance sigma squared. And we could draw it in this form. So this one has a sort of a mean. This might be a distribution over heights, although it's funny to use it as a distribution over heights because, of course, it has negative support. But actually, it's extremely unlikely to ever give you a negative value. It will never give you a negative value in this case because the tails are very light. They fall off very rapidly. So you're never going to sort of see a value out here, no matter how many times you sample, because it's too many standard deviations away from the mean. So there's the mean marked by a line, and the standard deviation in this case, I think, is a point. What's that going to be? So it's about 2. So it's about, well, it's the square root of that, 0.15, I think. So it's a nice looking, and it's often called the bell curve. And often, does anyone here teach? You know, you're often told, why aren't your marks Gaussian? And it's very easy to make your marks Gaussian. You just ask many, many, many questions, and then eventually the central limit theorem applies, and you get Gaussian marks. I know I tried it, and it works really well, and no one asked about why my marks weren't Gaussian then. So it's got 2 really important properties which will come up. the first of these is sort of like, I don't know, I think the first time you hear it, you're like, yeah, okay, that's fine. But actually, it's a really rare property of a probability distribution. So the sum of a Gaussian random variable is also Gaussian. So if yi is drawn from a Gaussian with mean mu I and variance sigma squared I, then the sum of yi's is also Gaussian distributed. And the mean is the sum of the means, and the variance is the sum of the variances. This actually turns out to be important philosophically, because if you think about when you're averaging things, people initially, before they knew this, they didn't like the idea that you should average measurements, because they would say, well, one of those measurements is right and then some of them are wrong, and if we bring the wrong things in with the right, we'll just make the whole thing wrong. And this property here is actually why that's not true if things, well, even when things aren't Gaussian distributed because of central limit theorem, but you can sort of see it here, that if you were to average y's, if these were samples from the same distribution, divide by n, well, the noise, the variance is, the square root of the variance is sigma I, but the standard which is the sort of standard deviation, which is kind of the standard error, but the standard deviation of this person is the square root of the sum, not the sum of the square roots. Yeah, and that's different. So that by summing all the variances up and then square rooting, and in fact, if you look at the mean, you'd have to divide this by n, you find that the error decreases as you add in by square root of n. And this is just to show how sort of kind of rare this is. There's other distributions that have this property, that they sum and they stay in the same family. But all those distributions and all the distributions that don't have this property, this is rare because actually most distributions that have finite variance tend towards Gaussian. So if you do this to other distributions, then they also tend to this distribution over time as you sum measurements up. So that's the central limit theorem that says that it doesn't matter what, even like these uniform distributions, if I sample from a uniform of 0 to 1, then as I sample from those and add them up, eventually I get a Gaussian distribution. And that's why de Moivre was looking at the Gaussian as an approximation to the binomial, because it tends, as you get more observations, to become Gaussian. So it's a very unusual sort of property. This one is kind of not so unusual. Lots of distributions do this. If you have a sample from a Gaussian with mean mu and variance sigma squared, then, and you scale that sample, then it's equivalent to looking at a sample with the mean scaled, so the mean of this distribution is scaled, and the variance squared scaled, so the standard deviation scaled, right? So if I multiply a Gaussian sample by 10, and the original standard deviation was 1, the new standard deviation is 10, and the new variance would be 100. OK, so they're sort of simple things, but they'll come back in as we go forward. So that's all very well. But actually, I'm interested in what we've talked about so far is this situation where I've got a model, I've got a function that I believe in, and I'm corrupting that model with my observations by some noise. But what I want to look at now is an underdetermined system. So this is, to me, why I love probabilistic approaches to machine learning and statistics and whatever. Because you can deal with this. So what if you just had one observation? So you wanted to fit y equals mx plus c, and you've got one observation of y1 and x1. Well, you can certainly compute, sorry, there should be an x1 on the bottom there. You can certainly compute what m would have been if you knew c. So conceptually, sometimes I like to think of this. Here's our observation. We'd like to fit a straight line to it. So that is a straight line that is consistent with it. That's another one. That's another one. That's another one. So we've just taken some values of c, and we're fitting the corresponding straight line. So how am I doing that? Well, I'm doing the same thing. I'm just going to say, in this case, before we said the noise corruption, which is the sort of way that our model departs from our observation, we're going to use a probability distribution to represent that. In this case, I'm just sampling for each line I create, I first sample a value of c, and then I fit the line through it. So now I'm getting a distribution over the lines that fit through my data. That's interesting because my understanding is for Laplace and Gauss, doing this type of thing was very, very natural. But this became considered an unnatural thing to do because people took the point of view that the first latent variable that Laplace introduced, epsilon, is associated with what they would call aleatoric uncertainty. So if you're making observations of planets in the sky, you've got noise that is brought about by the atmosphere fluctuating, thermal noise. And that noise, one would argue, or the aleatoric uncertainty says, is, well, that's noise that is truly uncertain. It's something that I can't determine. Because just as Laplace said, it's noise arising from movement of vapor, well, not vapor, molecules of air, which he said is, oh, we're ignorant about that. Whereas sort of statisticians around 100 years ago were saying that this is a parameter itself, c, and that our uncertainty about it they called epistemic. And they said we shouldn't put probability distributions over that. And that's the big Bayesian frequentist controversy. It doesn't interest me very much apart from historical reasons, because my point of view is kind of similar to Laplace's, is that if you've ever got something unknown, you can always treat it with a probability distribution. And that's the sort of modus operandi I follow. What that means is, what we're sort of saying, we're starting to say something not just about the noise on the output, but we're going to start saying things about uncertainty on this function directly. And that's what Gaussian processes will turn out to be for, is allowing us to talk about uncertainty on this function directly, which is not the classical approach of doing machine learning. And I think it becomes very obvious when you work with Gaussian processes, because they take these very different forms from classical approaches. OK. So that's how we dealt with the overdetermined system. We turned it into an underdetermined system and added a distribution. So we said that this corruption is drawn from a distribution. In the underdetermined system, we introduce a distribution for the parameter c. There's a slight difference because in the overdetermined system, we are introducing n parameters, one for every observation of the data point, and we're saying they're each independently sampled. Whereas here, importantly, we're saying that there is only one parameter, and we just sample it once. What that's going to do is it's going to induce correlations over all our predictions. And those type of correlations are what lead to Gaussian process functions. So it's known as a Bayesian treatment. So the first type of uncertainty we talked about, I said, was aleatoric, and this is epistemic. Here's my favorite way of separating aleatoric and epistemic uncertainty. If you watch a football match live, you are uncertain about the result, and that is aleatoric uncertainty, right? If you are watching a football match that you've recorded as if it's live, which is very difficult to do nowadays, because all the internet tells you all the scores and everything else. But in the old days, you used to be able to watch a recording of a match and pretend it was live. It was just as exciting, but your uncertainty was no longer aleatoric, it's epistemic, because in principle, you could go and look up the result. The result is known. Now, I guess there's a sort of, these two come together because you can argue that there is nothing genuinely stochastic going on in a football match, that there's everything that's going on in the Laplace type way is all deterministic. And so then you can say, well, everything's epistemic. But in practice, we know from chaos theory that the precision with which you would need to know the initial conditions of every constituent element of the game is sort of beyond our capabilities. So in that sense, it is always unknown. But to me, it feels like the type of uncertainties are broadly the same. But it is a sort of big philosophical discussion that Yeah. Okay. Right, so let's look at Bayesian regression. So Bayesian inference requires this prior probability on the parameters, and that's the belief we have about those parameters before we see the data. So it ends up fitting in our model. It's not in our data, it's part of our model. So for linear regression, we can consider a sort of prior on the intercept. And what we do is we typically combine the likelihood we had down before. So that's the probability of y given c in this case. Remember we had the Gaussian likelihood, which was saying that the noise was, the mean function was f of x. Here that f of x would be y equals mx plus c. So c is a parameter in that likelihood. And there's other parameters too, but just for clarity, I'm just putting that one parameter here. And we put a probability distribution over that. And we use this extremely complex rule called Bayes' rule. I mean, it's not complex at all. It doesn't even really deserve a name. It's just the product rule, right? If you move that on that side, then you're just saying that P of C given y times P of y, that's the joint distribution, P of C comma y. And on the other side, P of y given C times P of C, that's also the joint distribution. So apparently you have to name it if you divide both sides by P of y. But what's important about it conceptually is that it's allowing us to convert from this y given the parameter to what's the new distribution over the parameter given the data. It does so, okay, we recover the P of y by marginalizing the joint distribution over C. So if you integrate this over C, then you get P of y. And that's the headache with Bayesian inference. If you ignore that, it's the proportionality, it's just that which is multiplication, right? So to sort of see it conceptually, I like this sort of plot. So this is our prior distribution. I've actually made it non-zero somehow. I've said 0 there, but it's not. It's non-zero. This is the prior distribution over C. And then I'm going to make an observation. So I'm going to plot the likelihood. Oh, press the wrong button. So this is the likelihood. So now, be careful. This is not, in general, a distribution on this axis C. It looks like a distribution here because of the form of the Gaussian. So if we go back to what the Gaussian looks like, the Gaussian's unusual in, well, I guess other distributions have this property. Because mu and c is appearing in here, because what we're doing is we're substituting the mean function with mx plus c. So c is appearing as y minus mx minus c. So c and y are appearing in this argument sort of symmetrically, right? So it turns out that if you were to do a distribution over C, you could argue, oh, this is a probability distribution over C with a mean of y. And it would look the same. But that's unusual. That just happens to be the form of the Gaussian. So that's why you see something that looks like a Gaussian distribution in your likelihood. Oop. Oop. Okay, so it looks like a Gaussian, but this doesn't need to be normalized in this space C. It's a function of C. It's probability over y, and we're not visualizing it in y at the moment. Y is giving us the sort of equivalent mean in this case. And that's a Gaussian distribution with a mean of mx plus c and a variance of sigma squared. And then what we do is, to get the posterior, we multiply these two together, the prior times the likelihood. But that's not all. We actually then need to normalize. So if we were just multiplying the prior times the likelihood, we would just get, look, this is about 1 here on this axis. So the new distribution would be up to here. But we don't just multiply, we normalize by the marginal likelihood, because if we were to just multiply, we wouldn't have a probability distribution. Well, the math tells us that we have to normalize, but conceptually, if you'd have to renormalize to make sure that this is a probability distribution. So this is a scaled version of the multiplication between the two. And that's its form. So you can do the math behind that. Don't worry too much about it. But the important thing is that the posterior distribution, if the likelihood is Gaussian and the prior, so if the likelihood is Gaussian and the prior is Gaussian, the posterior is also a Gaussian distribution. And that's another unusual property. Most distributions, well, in many cases, if you multiply two randomly selected distributions together, you don't even have a tractable distribution as a result. So generally in Bayesian inference, people use conjugate pairs where the prior and the likelihood are conjugate, meaning that when they combine together, the posterior is the same functional form of the prior. The Gaussian is further unusual because its conjugate pairing is around a Gaussian likelihood as well. The marginal likelihood also turns out to be Gaussian. Now, why does this magic happen? The magic happens because Gaussians have this exponentiated quadratic form. That they're of the form of the exponentiation of a quadratic, and if you multiply the prior, which is the exponentiation of a quadratic, times the likelihood, which is an exponentiation of a quadratic in C, because C is the mean, you get something that is still the exponentiation of a quadratic by just the laws of exponentials. So that's kind of unusual. Normally when you multiply things, you don't stay within the same functional family. And that's why Gaussians, it's another reason why Gaussians are sort of very nice in practice. Of course, that's a sort of univariate Gaussian. For the multivariate case, we actually have more than one parameter. So for the multivariate case, where we've got many inputs, then we weight each of those inputs with a separate parameter, wj. Now, I prefer to write that in vector form. So we just get a vector in a product. So in this case, I've dropped c for convenience, but I can always recover it by just having one of my inputs set to be the constant value. That's a common trick. So this is actually a special case of the equation before, where we could set the first, so x is now a vector. We could set one column of x to just be the original x, and the other column of x to be 1. And that would give us w being a vector of m and c together. So this is the sort of same form as before. But when we go to this case, we need a prior over w, which is a multivariate Gaussian. So we can do a multivariate regression likelihood. Instead of the f of x here now, I've got w transpose x. And we need a multivariate prior. So this multivariate prior at the moment is actually, it's not clear because I've used the inner product here, but because in here this is a sum over the w1 times w1 plus w2 times w2. This is basically an independent prior over w. But what happens in the posterior is things become correlated. So to give you a sense, I'm mainly about, I know this is a review for a lot of you, but it's mainly for me about intuitions. I'm interested, I like, I mean, for me, the thing I really like about Gaussians is the way they express correlation. But for the moment, let's just consider independence. So if we have a distribution of height of a population and a distribution of weight of a population. So here, this is the same thing we saw before, 1.7 meters, and this one is centered around 75 kilograms. Then I can build a joint distribution by just assuming independence, P of W times P of H. This is your classic assumption. That's the definition of independence, that the joint distribution factorizes into W and H. And if I sample that, what that's equivalent to doing is taking a sample from the height distribution and a sample from the weight distribution. So what I'm doing here is plotting those. But in practice, we know that's wrong. So actually, the body mass index was developed by a guy called Adolphe Quetelet, who was interested in applying physics to society, but he realized you couldn't use laws. So he's one of the sort of fathers of statistics, and he did a lot of measurement of people. He came up with the idea of the average man and did a lot of measurements of different people in order to try and represent them. And one of the things he invented was the body mass index, which was originally called the Quetelet index, or Quetelet, I guess, because I think it's a French pronunciation, which is defined as W over H squared. That's supposed to reflect the fact that the taller you are, the heavier you are. So in practice, we don't have the capability to independently sample a height and a weight. We need to jointly sample them. So what I've done here is I've drawn a correlated Gaussian. So this is one contour. I should have explained this before. If we multiply that distribution in the weight axis by that distribution in the height axis, we got the circle from before. Here, you can't achieve this by multiplying them together. What you're seeing is a correlation. And in this case, you expect people who are lighter to be shorter. Of course, it's not universally true because there's sort of noise around it. So now when we sample, we generally expect data to come in these up here or down here. We can still get data off the axis because it's not that the distribution in this direction is sort of totally tight. But importantly, what we see is the marginal distribution. I'll talk about this a bit more in a bit, which is the view. If I were to look at this, this is a contour of a Gaussian bump. If I were to look in this direction, then I would see that density. And if I were to look in this direction, I would see that density, because I would see these contours here at the two sides, or these contours here from that direction here. But I would have seen the same here, but in this case, there's no basically, I'm seeing the whole distribution. I'm not seeing the fact that these things are twisted. So we can sort of think of, and the way I like to think about that is it helps me understand some intuitions about the Gaussian density. If I assume weight and height are independent, I can multiply the distribution of weight and height together, and I recover this sum in the exponential. It's exponentiated quadratic again, the sum of two quadratic forms. And of course, these are the normalization constants of the Gaussian, just popping out the front. But if I rewrite that in vector form, oh, I was trying to zoom in, but I don't seem to be able to. OK. If I rewrite that in vector form, so what I'm saying here is I've got a vector, WH, and a mean vector, mu1, mu2, and I'm subtracting off here. And then I've put this diagonal matrix here, which I've said is an inverted diagonal matrix. So I can rewrite that in vector matrix form. And now I can sort of say, OK, if this is a diagonal distribution, I've got a vector mu, which is my mean, and this diagonal inverted is this diagonal is my covariance, and I invert it here because it was dividing by the sigma squared. So that's just a mathematical rewriting of the independent distribution. And I've called W and H, the vector of them, Y, the combined vector of them. This object out here, I recognize that the product of the diagonals of D is actually the determinant of D. So it turns out I can rewrite this product here as the determinant of the matrix 2 pi d to the half. Now, if we go back to the plot before, you can see that we can conceptually think of going from that situation to this situation as just a rotation of the space. So we can think, there's actually some space in which I could look down here and look down here, and things would look independent again. So if we say that the rotation of that space is represented by the matrix R, we can just conceptually think of doing that mathematically. So I'm going to introduce a matrix R to rotate that space. And everywhere there's a Y and a mu, because I have to rotate the mean as well, I'm bringing in R. But once I've done that, I can actually pull the R out the other side. And I can recover this. R d to the minus 1 R transpose. That is what I call the covariance matrix. And one way of thinking about the covariance matrix is it's a diagonal matrix of independent variables rotated to find that twisted matrix. Reversing that operation is actually called principal component analysis. So the operation of PCA says, let me empirically estimate the covariance matrix and then diagonalize it. And what you recover as the eigenvalues is the diagonals, and the eigenvectors is R. So the principal directions in PCA would be these axes here. They're chosen to be orthogonal because I've said let's do a rotation, right? But I could do any affine transformation. So any affine transformation, and there's a sort of infinite affine transformations which would have the same effect on that original distribution. So for that reason, we choose the one which is associated with orthogonal axes. All the other ones are sort of have non-orthogonal axes, and that gives us a unique solution. And those axes are the principal axes of this ellipse, therefore the principal components. So very much the covariance matrix is defining that shape of what that twist is, and it's defining it in a. Remember, the covariance square rooted is the standard deviation, right? So the standard deviation would be kind of the square root of this object here, which would just be r times sigma squared square rooted, so it'd be r times sigma. So it's just those original standard deviations rotated. Yeah? So you can sort of think of that as being the basis of which you're moving everything around from starting from a spherical Gaussian. OK, it turns out that I can just substitute. If I know this to be true, then the determinant, if I rotate a system, its determinant doesn't change, because the determinant's measuring the volume of that system. So one way of computing the determinant is to diagonalize and take the product of the diagonals. So basically, I can just substitute in here for d to the half. I can just put c to the half directly. And that gives us the form of a multivariate Gaussian. OK, so we've done it in 2 dimensions, but of course all this applies in very, very large dimensions. And this is where things get really, really interesting, because the covariance matrix contains a lot of information. So when I was at high school and I didn't like Gaussians, it's because I didn't know about multivariate Gaussians and covariance matrices. So what people tend to think of with the Gaussian is they think of like what Gauss did first time. They think of, I need to estimate some noise. Things are independent over my data points. What goes on in a Gaussian process is you start playing with this object where you're saying, I've got dependence between all my points in my process at all times. And this is, I mean, you can put mean functions in, and there are reasons to, and let's not totally trivialize it. But for me, 99.9% of the interest is in the covariance. And designing of your covariance is how you build your model. OK. I'll just do the properties of the multivariate Gaussian, and then I'll pause and just check if there's any questions before I introduce the GPs. So remember the univariate Gaussian properties is that the sum of yi was distributed as a Gaussian, with the mean being the sum of the means and the variance being the sum of the variances. And scaling a Gaussian leads to another Gaussian. Well, those 2 properties together lead to this lovely property for the multivariate Gaussian. So if x is a vector drawn from a multivariate Gaussian with mean, so if x is k-dimensional, the mean is k-dimensional, and the covariance is k by k, if it's of that form, and I'm interested in y, which is equal to wx, where w is an affine transformation. If w is deterministic, then I know that y must have this form. So y has a mean of w times mu and a covariance of the form w c w transpose. That's actually a little bit what we just did before, right? Because we just rotated the diagonal covariance, and we came out with the covariance r c r transpose. But in this case, I've done a full affine transformation, so that's not a simple rotation. And we get this object out here. Now, that doesn't maybe seem that exciting to some, but you can view this as the following, and we will do. You can view this as a prior distribution over some variable you're interested in, x. This is a probability of y given x. Certainly, if I add noise, it would be a probability. It's not really a probability at the moment because it's just an affine transformation of x. But conceptually, it's telling me what y is given x. And this is telling me the probability of y. Right? With just using very simple properties of multivariate Gaussians. Now, I briefly mentioned earlier that going from the joint distribution P of x comma y to P of y requires marginalization of x, right? So what you're doing here is a multivariate integral. Multivariate integrals are in general very, very hard. So we can make x 25 million dimensional, and this is still true. So multivariate integrals, high-dimensional multivariate integrals in Gaussians are utterly trivial. And the reason they come up so much they come up in a range of domains is one technique, which is the Laplace approximation, to dealing with a multivariate integral is to fit a Gaussian to the thing you're trying to integrate and integrate that instead. So it's a remarkable thing, because typically in Bayesian inference, we get real problems when we've got high-dimensional integrals to do. That's why we end up doing Markov chain Monte Carlo, all these sort of nasty complex things. But in the Gaussian case, it's really trivial. And it doesn't even require knowledge of integration. It just requires knowledge of this property here. So we can sort of relate, as long as it's a linear transformation. As soon as it becomes a nonlinear transformation, you get headaches again. OK. So yeah, here's very quickly. Probabilistic PCA is a model which says that y is equal to some affine transformation of some latent variables x plus some noise corruption. We could just use these formula, and if we set c equals to I and epsilon equals to be a diagonal sigma squared I, that would recover the marginal likelihood for probabilistic PCA. You don't need to do any integration. To do the posterior, which you're also interested in, you need to do some work. But it's just like 2 or 3 lines in linear Gaussians. Oh, and then we can look at also, say, neural network systems. So, or basis function models. So people are into neural networks nowadays. Here's a basis function, which I think of as the neural network. You can think of that as an activation function. And a neural network with one hidden layer is simply your output is equal to some basis functions inner producted with some vector of weights plus epsilon. So you can immediately do, if you say that you can turn that into a data set where your output, you can turn this into matrix notation. So this is for an individual data point. So for all data points, we have a vector y. And then we're going to use our basis functions. We orientate them in the form of a design matrix, which I'm calling phi. If we write it in that form, and then we say that, epsilon is drawn from, so we've got a noise distribution of that form. Then we define a prior distribution of this form. We can immediately write down that y is Gaussian with 0 mean, a covariance matrix of phi transpose. Now, I did say I wasn't going to use the board, but now I'm tempted to, but I can't. So I'll just wave my hands around a lot, because that will help. So just to sort of emphasize what's going on here. This vector, this representation, you might not have seen it before, is saying, OK, I've got this is true for one data point x, right? So if x is a vector, but then it's going into a basis function, this is also a vector. This form here is assuming that I'm going to lay out all my data points, one on top of the other, into a long vector y. So it's n-dimensional. It's n by 1. This matrix here is take the features for each of those data points and put them in the rows here. So it's n by k dimensional. And this vector here is k by 1. So n by k, k by 1. And multiplying them together gives me a n by 1. Epsilon is n by 1. So remember that. That's n by k. It's got the features, across every. So the activation functions in the neural network, it's got their values across each row of the matrix. That means that this matrix is an n by k times a k by n transpose. So this is an n by n matrix. OK? That plus sigma squared I is also n by n. So this is a sort of, it's a matrix in a product type object, which is rank k. But then this thing makes it full rank. What we see by that simple law is that we're saying that y is distributed as a Gaussian with 0 mean. The mean is 0. That's important. But the covariance has this sort of low rank form. And it turns out when you write down a basis function model or a one-layer neural network, if you are happy to have a Gaussian prior over your output weights, that's what you're saying. You're saying your data is jointly Gaussian. Once you integrate out W, you see that you are specifying correlations which are coming from this object here, which is the covariance matrix. That covariance matrix K, I can write in this form here, or I can try and rewrite it in this more classical form that we use in Gaussian processes, where I look at each of these elements here of phi is taken by multiplying one row, which is the function of xi, by another row transpose on here, which is a function of xj. So each element here is actually just a function of xi and xj. That's what we call the covariance function. So in the case of a neural network, doesn't matter whether this is ReLUs or radial basis functions or whatever, what we're saying is that the elements of the covariance function are given by the inner product of the basis of the activation functions applied to one data point with the activation functions applied to another data point. And that's telling us how they're correlated. OK. Let me pause there and just see if there's any questions at that point. In which case, so I have to admit, I don't believe in aleatoric uncertainty. It's because I don't understand quantum physics. So I may have conflated them. But in which case, which was aleatoric?
I can't remember. Because,
OK, aleatoric is the one which is genuine stochasticity. So like the idea of rolling a dice and getting an outcome. So people think of that as generally stochastic. It isn't, of course. It's deterministic. But it's so hard to measure in the Laplace sense, you know, that, oh, I can't measure these things. It just seems impossible. So people call it genuinely stochastic. But kind of a Bayesian doesn't make any distinction. They just say that these things are all the same. So the controversy around Bayesian inference is around philosophically saying something like, if the match has already happened, if the football match has already happened, I still want to use probability over the result of that match, even though it's a known outcome. And that's, so Fisher didn't like this. So he's a statistician from the 1930s. He didn't like this, and he did a lot of work to try and create division between these approaches to probability. But I wouldn't worry about it too much. What was the exact confusion? I didn't...
well, I just didn't understand what was happening over there.
So you don't, if you don't understand the difference between aleatoric and epistemic uncertainty, then you're natural Bayesian. I think Tonio Hagen has this thing. Everyone's born Bayesian, and they get educated out of it. So I don't want to educate you out of it. Because I didn't really understand it. But people, it's just a sort of thing in the background. I mean, I do think that there is something... yeah, I don't get it either in some sense, because it feels naturally to me that you could treat both with uncertainty. And work by Cox and Diffinetti shows us that we can, right? That we can use probability to represent unknowns. It doesn't have to be a truly stochastic system for us to use probability. Andre.
So about the rotation matrix R. So it's clear the intuition behind this matrix from the rotation point of view, but from the relations of the input point of view, what's the intuition behind the R? Because you can just say it's like we are just rotating the space, right? Does it give any like is there intuition behind it as a relation of weight and height?
It's a really good question. I think there's an intuition behind it in terms of weight and height. It's giving us the principal axis, the direction of most variance. So it's sort of PCA was actually developed by well, an algorithm equivalent to PCA was developed by Pearson before Hotelling called it PCA. And he was looking for an algorithm that said, if I want to predict height from weight and weight from height symmetrically, so I'm not doing regression, I'm not trying to predict height given weight and weight given height, I'm trying to have a symmetric prediction. What's my optimal line of prediction? And that also turns out to be the principal axis. So it sort of has that intuition behind it. If you've got variables you're interested in that you're rotating. But I think a lot of these intuitions don't work when you start looking at processes. If I start looking at a whole data set, particularly in the nonlinear case, and I start saying, when we look at covariance functions, when we look at them later, that intuition doesn't really help. It actually starts giving me the span over which my basis functions, how they cover the space. I'm not sure that's super intuitive, but I'm trying to just give the sense in terms of where the covariance matrix comes from, rather than the intuition about a particular data set. There was another question, yeah?
Yeah, I was just wondering if you could speak to why Gaussian, you gave us a bunch of properties. Is it just because the properties are great that we choose to work with?
Yeah, I think broadly that's most of it. I mean, so I like to think of, there's a lot of stuff we want to do, right? And we can write down mathematical abstractions of a lot of that stuff. But in practice, we can't do them analytically. So what you tend to find in practice is, although everyone talks about lots of complex things, they're all stuck with the same maths that works, right? So if you go into kernel methods, they're using very similar maths to what we use in Gaussian processes, but they have at the core a different motivation. But linear algebra works. I think there's a lecture online from Philip Hennig, who did one of the introductions here, where he almost pushes Gaussian processes on that basis. He says, well, we've designed computers to do linear algebra, pretty much, so why don't we use Gaussian processes to do the inference? Now, there's problems with that because, of course, when we're really modeling things, they may not capture the actual thing we want to model. But one of the things I've noticed with Gaussian processes is people say things like, I'm not using a Gaussian process because my data is not Gaussian. And then they explain the model they're using, and they're using a Gaussian process. They just don't know it. So if you use a basis function model of the one I just described, a one-layer neural network, you're effectively using some variant of a Gaussian process. Signal processing models that assume bandwidth limitations, you're effectively using some variant of Gaussian process. Kalman filter is a variant of a Gaussian process. The reasons why all these algorithms are a variant of Gaussian process is because that's the math that works. I mean, unless you go discrete, and then you've got Markov chains and this sort of things, then analytic things are hard to come by. So by one token, yes, that's one reason we do it. By another token, actually Gaussian processes exist a lot in the real world. So the universe is not a Gaussian process, but it was, right? So the cosmic microwave background, by the finest measurement they can make, is a Gaussian process. And the parameters of the Gaussian process are like the fundamental cosmic parameters, like the amount of dark energy, the amount of dark matter in the universe, and the amount of real matter. There's 6 of them or something. So at one point, the universe was a Gaussian process. Why? Because it was very, very hot. And it was coming out of a plasma, and things in that state, they tend to be Gaussian. So the forces that were drawing things together were weaker than the temperature of everything moving around. Now, what we see now is a product of that Gaussian process having gone through a bunch of nonlinearities. So by one token, everything we observe is a nonlinear mapping from a Gaussian process to the present. But that nonlinear mapping screws up all the maths, annoyingly. But then that's why, so that's actually why we look at things like deep Gaussian processes.
What would be different if we choose not to rotate our diagonal matrix and just leave it in a nice little diagonal form?
So everything would be much quicker and utterly meaningless. So if you leave it in a diagonal form, it's always something that strikes me as unusual. We're taught to treat our data as IID. If your data was independent and identically distributed, you could learn nothing from one data point given another because it's independent. So never say your data is IID. What you really mean is your noise is IID, right? So the noise corruption is IID, plus the sigma. And when you just assume that and you don't start playing with the model, everything's much faster. You can do stochastic gradient descent, you can do all sorts of things. But you're not putting uncertainty into your modeling parameters. So you can't do the thing I'm about to do with this plot here. Yeah. Not easily. You can't do it analytically, I should say. OK, so this is a sort of way of visualizing Gaussian processes that Nicola, who's at the front, uses. So this is actually a Gaussian process. So these are a bunch of functions sampled from a Gaussian process. Of course, the functions are infinite length, and I only show finite things. I think you learn how to do this in the lab. But there's 4,000 of them here. They take a long time to render, so I'm going to move forward while I speak. What we're interested in doing is combining the model, so we have a mechanism of producing these functions, right? And what I'm interested in doing is combining those functions with data. So hopefully when it's finished rendering, because it's an SVG and there's 4,000, and I need to fix this in my slides. But there's 4,000 lines it's trying to draw. Maybe I'll just go forward one more. OK, so I got rid of them. I'm just keeping the lines that are consistent with 3 data points. So there were 4,000 lines, and I'm saying, just give me any line that goes through these 3 data points. And I'm left with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In fact, I think I chose the 10 closest. That's the way in Bayesian inference you're combining model with data. So you have some mechanism of generating functions, and then you say which of those functions are consistent with my data. So we can think about that as multiplying. That's mathematically, that is multiplying prior by likelihood. But conceptually, you can look at it as rejection sampling or a variant of importance sampling, where you generate many, many functions and throw away those that don't go near your data, where near is defined by your likelihood. The higher the noise in the likelihood, the further away these functions could be. The amazing thing about a Gaussian process is all those properties we talked about earlier, that when we were just asking why Gaussian processes, mean that we can do this analytically. So most of the time when you're doing it, there's an algorithm called ABC that Rich, who's speaking after me, is someone who's done a lot of the foundational work on, where you actually do that in practice, where you say, I've got a very, very complex prior, and I believe the world works like this, and I've got a load of code. I'm going to sample from it, and I'm going to throw away samples that don't fit my data. And then that's my posterior. And where fit, in that case, is where all the art is. But in the Gaussian process case, you can do this by linear algebra. And that's very, very powerful. So, I mean, another answer to the question from before about why Gaussian process is that you can push these uncertainties around through the system. So most other approaches, you kind of, either you go down the Markov chain Monte Carlo route, or you might say, OK, I'm going to ignore the uncertainty in the function at outset. I'm going to build a very, very complex function. And in neural networks, you see a load of work now where they're trying to put the uncertainty back in at the end. So I tend to take the opposite view, and I just love these error bars and the fact that they can represent quite complex functions. So although it's linear Gaussian, linear doesn't mean linear in the function space. It means linear in the parameters. So the functions themselves are non-linear. It's not a universal set of functions. There's certain things that are difficult to do with Gaussian processes. Like you can put jumps in, but you can't have infinite jumps that could occur at any moment. You can't have non-parametric jumping. But they're very, very powerful non-linear functions. So that's the sort of way a fit looks like. How am I doing time-wise? I've got 15 minutes. OK. I'll just quickly do this bit then. So where do those things come from? I said I sampled a function. So OK, let's pretend I didn't show you that. And let's instead look at this, this is a covariance matrix. This is going to flip in a bit. Apologies for this. Here, black is high and white is low, which is the wrong way around. Apologies. So what we're saying is I'm going to sample one 25-dimensional vector from a Gaussian. OK? That's one 25-dimensional, not 25 independent samples from a Gaussian. Like I'm sampling, like I did the height and weights jointly before, but now I'm sampling 25 things at once. And I'm going to plot those points against their index. So let's do that. So this is what it looks like. Oh. Go back to that, sorry. So this is what it looks like. This is 25, 1, 2, 3, 4, 5, 25 dimensional vector sampled from a Gaussian. The Gaussian has this covariance matrix, which is negative of what it should be. Apologies for that. And what this is saying, though, these are the indices of the covariance matrix. So it's saying if 2 points are close, they have high correlation. And if they're far, they've got low correlation. In fact, this is dropping to 0 here. So if I take the first 2 points in this plot, those two there, and I'm just giving you here, that's the covariance associated with those 2 points. Now, another weird property of Gaussian processes, if I want to integrate across F3 to F25, if I want to integrate all those out, it's, again, trivially done in a Gaussian process. All I need to do is focus on the covariance for F1 and F2 only. I can ignore the rest. So if I want, so focusing on that covariance, which is all black because these values are so high, they're 1, 0.986, and 1. So that's the covariance between these 2 points. Very, very highly correlated. It's another odd property that I can just integrate these out and it doesn't affect the parameters of this marginal distribution. That does not normally happen. And that's the reason why we can make it a Gaussian process. Because conceptually, I've implemented F3 to F25 out, and I just have to look at the covariance. Here, by the way, this is zero mean, so I forgot to emphasize that, and it's super important. This is a zero mean Gaussian, right? So if we sample from this 25 million times, an average, we'll get some line close to 0. Because although that is going up and down, there's another function that goes down and up like that to match with it somewhere. So the only parameters of this is this covariance, and this is the parameters of those F1 and F2. But conceptually, I integrated out F3 to F25. I could integrate out, say I'm integrating out F26 to F infinity. All countable future variables can be integrated out, and that's still the covariance between these 2 points. Does that make sense? That's how we start getting into the regime of being able to create processes, because this form, this covariance function, allows us to only consider the points that we have at any given time. And that's what we're going to do next. We're going to consider 2 data points. So what I'm showing you here is the contour of the Gaussian between F1 and F2 with this as the covariance. So very high correlation, higher than we saw before for height and weight. And now I want to sort of teach you how you do test predictions in a Gaussian process. So let's assume that I see a value of F1. So that's the value of F1 I'm going to assume we've seen, this pink line here. The conditional distribution of F2 given F1 conceptually can be found by, this is like a Gaussian hill. We're slicing through the Gaussian hill, and the form of the conditional is the form of that slice, renormalized. Right? So this is gone off the picture, it's up here. So this is the conditional distribution of F2 given 1. What is this saying? It's very natural. It's saying, look, if F1 is negative, the chances are F2 is also negative, but it's varying around these 2 standard deviations. So those remain the standard deviations once that's happened. It's not if, by the way, if I were to, this is actually, because this is a covariance and this is, the diagonal is 1, this is a correlation coefficient. So if I were to set that correlation coefficient to 1, this would be a degenerate covariance, right? It would not be full rank. But as I tend towards 1, this variance here would disappear. So the principal axes would become just 1 in that direction and 0 off that direction. And in that case, the conditional distribution of F2 given F1 would be F2 is equal to F1. Yeah? So as these values drop off, that variance gets a little bit wider. Oh. So that's the distribution of F2 given F1. So if we had that covariance and someone told us what F1 was, we would now have a distribution over F2. And that's the essence of prediction in a Gaussian process. You have that covariance and you do that operation. Now, whenever I think of this, I always think of Uluru. I can't pronounce it properly, but I think of it, I don't pronounce it. So whenever I think of this hill, I like it because it's sort of arising out of a flat plane. And I know it doesn't look like a Gaussian. It's more like a sort of logistic with a logistic on the other side, which is also a valid distribution. But when you're looking at it from this side, you're looking at that Gaussian bump. You can't actually tell whether it's twisted away from you. So you're looking at the marginal distribution in this direction. If we go back here, if we're looking at this, and this was that hill, the marginal distribution is a variance 1 Gaussian, because the standard deviation here is 1. Similarly, if we look in this direction, it's variance 1. That's given by the diagonal, right? We look at the marginal, we just take out the other one there, we get the variance 1 Gaussian. But the conditional distribution, and you must never do this, don't go to this hill and do this, but imagine slicing through. So someone sliced that hill in that axis, and then that would cause, if that was twisted towards us, it would cause a little Gaussian bump. I don't know what its shape is from above, actually. But if it were twisted towards us, you would get a little Gaussian bump, and that's your conditional distribution. So the marginal is the sort of the full thing like that. And if someone were to slice through from that direction, the F1 direction, as it were, at some depth, we would get the conditional distribution. And that's geometrically what's happening when you do conditioning. Mathematically, it's done like this, that the conditional distribution is, the mean is given by F1 times K12, which was the off-diagonal element of the covariance, divided by K11. So in our case, this was 1, so it was just 0.986 times the original mean. The variance was, this is again 1, the diagonal, minus that off-diagonal squared. So 0.986 squared, so 0.9, something less than 986, divided by 1. So if K12 was 1, you would see that the mean would just be F1, because that would be 1 over 1. And the variance would be 1 minus 1 over 1, so it would be 0. And then as the correlation decays, we start to see larger variance. And just to illustrate that before I stop and check for there's another question. Here's the corresponding situation where we're looking at data points 1 and 8. Right? So if we look at data points 1 and 8, then the correlation coefficient's much lower, 0.5. Still quite a large correlation if we were doing a statistical test. But look at what happens when we do our conditioning. So here's the joint distribution. It's a much fatter Gaussian. There's the observation of F1. And there's the distribution over F8. It's much wider. So in fact, there's quite a high probability that you end up in the positive space, despite the fact that F1 was negative and these two are correlated. And indeed, if you look at the observed value, you see that the observed value was actually on the 0 line. So this line is coming from the fact that if I take any two of these points, there's a covariance between them. Not only that, if I take any three of them, there's a covariance between them, and so on and so forth. It's all of these points, if I move any of these points here, in theory, it affects any of the others. In practice, as I move further away, I had the correlations decaying. So it doesn't affect them as much as you might like, or you might believe. 1 point moving here will typically affect points in this sort of regime around here. So that's the way that we're describing our Gaussian process, by a series of correlations between matching points. And then just the last thing to finish from, because I think Nicolas will talk about this afternoon. But where did this covariance matrix come from? Well, I showed you one way that it could come from a neural network. But in general, the covariance matrices have this bivariate form. So they are a function of two inputs that gives me a matrix that is always positive definite. So sometimes that's known as a positive definite kernel. There's two inputs, one data point and a second data point. And the way we build this covariance matrix is element by element at a time. And we end up with something that says correlation between points that are nearby. So if 2 points are close, if this is 0, then the answer is alpha, e to the 0 times alpha. But if they're further apart, if L is sort of small or the distance between these two is large, then the correlation starts to decay away. And this is a very widely used covariance. It happens to have an exponentiated quadratic form, but you don't have to. Many covariances don't. And that's where that covariance matrix came from. Importantly, a lot of the properties of the smoothness we saw, so it turns out that the functions we're generating here, which is also from this covariance, are infinitely smooth. So that to me that's mind-blowing if you're used to sort of classical views of Gaussians, because people think of Gaussians and they think of noise, right? But that's when you have independence. You have this covariance structure that this function has no stochasticity in it, any single function, from the eye of the human. I mean, what stochasticity means in that context is a bit of a strange question. But from the eye of the human, it's infinitely smooth. A lot of people think of something as stochastic as being non-differentiable. This is infinitely differentiable. So you've got a process that can generate infinitely differentiable functions. Often you don't want that, and there are other covariance functions, some of which I'm sure Nicola will tell you about, which allow you to have processes that are not infinitely differentiable. But that's it. I'll stop there. I'll just maybe take 1 or 2 brief questions before we break.
In the expression you just gave, where you have this exponentiated quadratic, do we have to be worried about the scale of the values of x?
Yes. Yeah, that's a good question. So do you have to worry about the scale of the values of x? Yeah, if you don't get the scaling right in algorithmically on alpha and L, you'll hit numerical difficulties. A typical one would be L being too large relative to the scale, and this matrix becomes flat. It just becomes a constant value numerically, and then you hit problems. The other direction, if L is too large, this matrix becomes a diagonal. And when you're doing gradient-based optimization, because in practice you optimize with respect to alpha and L, you tend to find it's hard to find a gradient and find the optima. So in practice, one of the things I like to do a lot is take my data set and visualize what the covariance looks like. So the two, and for this particular covariance function, the sort of two extremes are diagonal and totally flat. And if you've got either of those, then you must have the wrong parameters. You don't really have structure in your data set. You can visualize a portion of it and see that. What you want is sort of structure in here, typically. You don't see structure in this case because it's a straight line. But for higher dimensional inputs, you'll start seeing sort of patches of clustering. And of course, I've ordered it, right? So you're seeing it's a straight line because I've ordered the data. If I were to disorder the data, you would see structure all off diagonals. So in GPy, the software that you're using for the labs, we made the choice. You can do some automatic scaling. You can say, please scale my inputs. But by default, we don't. Why is that? Because L has a sort of meaning, a physical meaning with respect to your inputs if they're unscaled. So somehow you don't really want to necessarily scale people's inputs because the length scale can have a real physical meaning. So we don't tend to do it by default, but you may need to do it in practice.
Location of these points is invariant in this case, right? So it doesn't matter whether it's 0.1 and 0.9. The correlation between points 1 and 9 is going to be the same as points 2 and 10 and 3 and 11.
Yeah. So that's actually that's a great point. So the question was, it doesn't matter. The correlation is the same. It's dependent only on the distance. It doesn't matter what offset I apply to x, right? So I can move x and x prime to the right by 7, and the distances between them is the same. And that's the property of a so-called stationary covariance function. So when you see something like this, which is only a function of the distance between the points, then in your data, then that's known as a stationary covariance. And that means the properties of the function don't change anywhere on the inputs, which is sometimes what you want. Other times you don't want that. Other times you may know about a non-stationarity. And there are covariance functions you can use when you know about a non-stationarity. Other questions? Someone can ask, can we have coffee now? No.
Yes, so we have coffee now. We'll start again at
So you have observations daily. And now, perhaps I want to use my model to predict something hourly or minutely or at second intervals, right? That's the concern I have about the scaling. Of course, you make these values smaller and you've got this nice sort of way